What is meant by water quality? Water quality is a very complex topic to define, as the criteria vary depending on the intended use of the resource. For example, for drinking water, the criteria include the absence of chemical and microbiological contaminants, while for water intended for irrigation, parameters such as salinity and the presence of nutrients are considered. For water intended to support aquatic life, parameters such as dissolved oxygen and temperature are evaluated. These criteria are essential to ensure that the water is suitable for its specific use and to protect both human and environmental health. The European Union Water Framework Directive, in addition to bringing together all reference regulations for water resources into a single regulatory framework, unifying for the first time the protection of different types of water, such as surface water, groundwater, brackish water, and water intended for specific uses, introduced several highly innovative elements, including the introduction of environmental quality standards, known as EQS, specific to each type of water body, and the move beyond the concept of discharge limits. Quality objectives, also differentiated by type of water body and the time frame for achieving these objectives. The economic analysis of planned interventions and the concept of disproportionate cost for the most critical situations. The Water Framework Directive, or WFD, defines water quality through physico-chemical and ecological parameters, taking into account the needs of aquatic organisms. The classification combines the chemical and ecological status, adopting the worst of the two as the overall quality status. Usually, the ecological status is worse because it is influenced by various factors in addition to the chemical status. The latter is determined by the concentration of priority substances, which are hazardous due to their toxic effects even at low concentrations. The ecological status is defined based on biological and hydromorphological quality elements, as well as concentration limits of specific pollutants that have a significant impact on aquatic communities. For each of the parameters used for classification, thresholds are defined corresponding to 5 quality classes: high, good, moderate, poor, and bad status. The WFD establishes that all water bodies in the Union must achieve good quality status or maintain high quality status where it already exists, within specific time frames. The guiding principle of the WFD is that water bodies should achieve good quality status. To achieve this goal, the directive provides that the existing national discharge limits may be made more stringent to address the most critical situations. In practice, once the threshold of the environmental quality standard has been set for a given parameter, the limits for discharges affecting that water body must be determined in such a way as to prevent even small sections from failing to meet the EQS, as for example happens in the case of the river shown in the graph. In fact, the graph shows the concentration of the indicator parameter in relation to the distance from the headwater of the river, which is ideally represented by the origin of the axis, and you can see that there is a polluted section that does not meet the EQS threshold. In these situations, it is not only necessary to take action on the last discharge point, 3, which causes the EQS to be exceeded, but for fairness, it is also necessary to reduce the discharges present upstream of the critical section. To assess by how much the discharges need to be reduced in order to comply with the EQS, it is necessary to have a river water quality model. River water quality models are able to accurately reproduce the phenomena and transformation kinetics of substances present in solution or suspension in the river. For example, they simulate the degradation of the biodegradable organic component and the corresponding consumption of dissolved oxygen, the reoxygenation of the river, biogeochemical processes of the main nutrients, as well as the phenomena of bacterial decay that affect the organisms present in the wastewater effluent. These models generally greatly simplify the hydraulic component of the diffusive and advective flow present in the water body and provide an average velocity that reflects with sufficient accuracy the travel time of the contaminant and therefore its transformation kinetics. The most commonly used approximation is the one that represents the river stretch as a sequence of computational units, within which a mass balance is simulated that takes into account the advective component, which drives the flow of dissolved substances from upstream to downstream, and the kinetic component, which considers their transformations. Within each computational element, the concentrations of the parameters are considered homogeneous, as are the geometric characteristics of the river section that the computational unit represents. With a simplified representation of this kind, it is possible to simulate the input of water and substances into the system both as point sources and non-point sources, as well as water withdrawals, which can also be either point or non-point in nature. In this way, models of this type are able to simulate the effects of interventions on the river. The graph shows, for example, the case of the Northern Lambro, in which the quality scores of several scenarios were compared. An average annual scenario prior to the interventions planned by the implementation of the WFD, a 2016 scenario in which it was assumed that the improvement measures had been carried out, and a further scenario that, in addition to the improvement measures assumed for the 2016 scenario, included irrigation reuse during the summer months for the effluent of some of the most significant plants. It can be observed that before the improvement measures, the quality of the Northern Lambro was unable to maintain good status downstream of the San Rocco di Monza treatment plant. With the interventions, the river remains just below good status up to the confluence with the Cavo Re dei Fossi, a canal that intercepts the waters of the Seveso River, which flows underground through the city of Milan. The scenario of irrigation reuse shows an even more significant improvement in the same stretch. Similar simulations make it possible to assess the effect on the river of a stream flow reduction or of an increase in temperature, which could be caused by climate change. A limitation of river quality models is that they are unable to adequately represent the biological component, which is an integral part of the river ecosystem. The images show larvae of aquatic insects, which form an important trophic node in the food network of the aquatic environment. The chemical status of the water body is very often the most limiting factor for this living component. The graph highlights the reduction in the ecological potential of a specific biological metric as a result of the deterioration of the chemical status. Without an improvement in chemical conditions, it is not possible to achieve a corresponding improvement in ecological conditions. Models make it possible to make informed decisions and to evaluate alternatives that optimize the cost-effectiveness of the planned intervention. The comparison examines two scenarios for the Lambro-Seveso-Olona basin. One scenario involves implementing a more effective membrane treatment at 8 wastewater treatment plants. The other assumes the same treatment is applied to all plants above a certain size. The 8 plants were selected based on their critical location and their resulting impact on the quality of the river. The bar chart, derived from the model-based scenario analysis, shows that intervening at these 8 plants is more efficient than a broader intervention, as it allows for an improvement in the river in terms of good ecological potential comparable to the wider intervention scenario, but at a significantly lower cost.